the ruins of a mud brick village on the west bank of the Nile at Luxor, modern instruments have recorded something that should not be possible. Interior air, 10 to 15 degrees Celsius, cooler than the desert outside. With no electricity, no machinery, and no moving parts. In 1946, when Egyptian architect Hassan Fathi proposed rehousing an entire community using nothing but sun-dried mud in a climate where midday temperatures routinely passed 40 degrees, his own government's engineers treated the idea as a step backward. Cairo had spent the early 20th century chasing concrete and steel, and mud had become a symbol of poverty rather than a 5,000-year-old engineering tradition. Fathi built the village anyway. People moved in. The desert summer arrived, and the houses stayed livable without a single fan. Decades later, when researchers finally brought sensors and data loggers into buildings like these, the numbers confirmed what Fathi had only been able to argue from experience. Ancient Egyptian builders had solved a problem modern concrete still struggles with, using nothing but river mud, shade, and wind. The problem those builders were solving was written into the geography itself. The Nile Valley sits inside one of the driest, hottest climate belts on Earth. A narrow strip of habitable land squeezed between two deserts, where summer highs regularly exceed 40 degrees Celsius by early afternoon, and temperatures can fall sharply once the sun goes down. Since dry desert air holds almost no humidity to trap heat after dark, that daily swing, punishing as it sounds, was also the resource ancient builders learned to exploit. A prevailing wind moving north to south up the Nile Valley for much of the year, driven by the pressure difference between the Mediterranean coast and the interior desert, gave builders a second resource, air that could be captured and redirected if a structure was shaped correctly to catch it. The river itself supplied the raw material for exploiting both thick, fine-grained silt deposited by the annual flood, mixed with chopped straw for tensile strength and shaped in wooden molds into bricks that needed only sunlight, not a kiln, to cure. Herodotus, writing centuries later, called Egypt the gift of the Nile, and nowhere was that gift more literal than in the walls people slept inside. Mudbrick is a poor conductor of heat, meaning a sufficiently thick wall absorbs the day's punishing heat slowly, delays it for hours as it migrates inward, and releases it back outward long after residents have gone to sleep. A property modern engineers call thermal mass, and one Egyptian builders appear to have understood empirically long before anyone had a word for it. The Nile Valley also gave builders a second, more violent weather pattern to design against: the Khamsin, a hot, sand-laden wind that blows up from the southern deserts for roughly 50 days each spring, capable of raising temperatures by 10 degrees or more within an hour and reducing visibility to almost nothing. A house that could hold a stable interior temperature against the steady daily heat of an ordinary Luxor summer also had to survive sudden, punishing spikes it could not predict in advance. And the same thick walls and small, high-set openings that worked against routine heat happened to double as protection against blowing sand and sudden temperature swings alike. Aswan, near Egypt's southern border, ranks among the hottest inhabited places on the planet, with July averages regularly pushing past 41 degrees Celsius and almost no annual rainfall to soften the heat at any point in the year. There was no rain to fall back on. Every drop of water available for drinking, farming, and construction had to come from the Nile itself, which is one reason Egyptian building technique and Egyptian irrigation technique developed as two branches of the same problem, rather than as separate crafts practiced by separate specialists. Orientation itself became a design tool. Builders across most periods favored fewer openings on a house's western face, since the low afternoon sun striking a west wall directly delivers far more heat over the course of a day than the same sun striking a north or east wall at a steeper angle. a detail visible across excavated house plans from the Old Kingdom onward, and one modern solar designers still treat as a first principle rather than a historical curiosity. The technique did not arrive fully formed. Egypt's earliest known settled communities, the Fayum, a culture active around 5000 BCE, and the slightly later Merimdi culture on the western edge of the Nile Delta. Built with reed timber and light matting, structures adequate for a semi-nomadic existence, but nearly useless against sustained desert heat. The Badarian and Naqada cultures that followed, spreading through Upper Egypt across the 5th and 4th millennia BCE, began experimenting with sun-dried mud plastered over reed frameworks, a transitional technique that let a household test the material's thermal advantages without committing to the labor of solid brick walls. Full mud brick construction. Bricks shaped in molds and stacked without a reed core appears consistently in the archaeological record by the time farming communities settled permanently along the Nile floodplain and needed shelter durable enough to survive a full year of extreme heat rather than a single mild season. By the time Egypt's first dynasties unified the country under a single king, around 3100 BCE, mud brick had already become the default building material for everything except royal tombs and temples, which used cut stone specifically because stone was scarce, expensive to quarry and transport, and reserved for structures meant to outlast a human lifetime by millennia. Ordinary Egyptians, from farmers to court officials, lived and died inside mud walls and the material's advantage for comfort, not merely its low cost, is likely one reason it never lost ground to stone for domestic construction across 3,000 continuous years of Egyptian civilization. Excavated remains from Naqada period settlements in Upper Egypt, dated to roughly 3,500 BCE, already show rectangular mud brick foundations, replacing the round or oval huts typical of earlier reed construction. A shift in floor plan that let builders share walls between adjoining houses and pack settlements more tightly, further reducing the amount of exposed wall surface any single room had directly facing the sun. Wall thickness mattered as much as wall material. Surviving foundations from Old and Middle Kingdom domestic sites show exterior walls commonly built half a meter thick or more, a dimension that has nothing to do with structural necessity, since a wall carrying only a light timber roof needs nowhere near that much mass to stay standing, and everything to do with how many hours a wall that thick could delay the day's heat before it ever reached the room inside. The clearest early evidence that Egyptian builders were designing deliberately for temperature, not simply building out of necessity, comes from a town most residents of ancient Egypt never saw. Kahun, built around 1895 BCE under King Senusret II. To house the workforce constructing his pyramid at nearby Lahun, was laid out on a rigid grid, a north-south main street crossed by 11 narrower lanes, precise enough that archaeologists still describe it as one of the earliest planned settlements anywhere in the ancient world. Those lanes were kept deliberately narrow, close enough between opposing walls to stay in shadow for most of the day, using the buildings themselves as a canopy over the street level where people actually walked, worked, and carried water. Houses throughout the town relied on thick mud brick walls and a minimal number of small openings, and even Kahun's internal social boundary, a 3-meter wide dividing wall separating the laborers' quarter from the officials' villas, was built from the same heat-absorbing material as every home behind it. Wealthier villas in the Eastern District went further, arranging reception rooms and bedrooms around a central hall open to the sky, so that even the grandest houses in town depended on the same basic shade and airflow logic as the smallest laborers dwelling on the other side of the dividing wall. Status changed the size of the rooms. It did not change the physics keeping them livable. Kahun was abandoned once the pyramid was finished, its purpose exhausted within a single generation. But the town preserves something more durable than the monument it was built to serve. Proof that by the Middle Kingdom, Egyptian planners were arranging entire settlements, street by street and wall by wall, around the physics of shade rather than leaving comfort to chance. A similar planned settlement appears again more than 4 centuries later, far to the south at Akhetaten. The short-lived capital of King Akhenaten, founded around 1346 BCE on a stretch of desert plain now called Amarna. Excavators found a dedicated workman's village there, walled and laid out on a grid much like Kahun's. Its houses packed tightly along narrow lanes, running north to south, to catch the valley's prevailing wind directly along the street, rather than letting it strike a wall broadside. The similarity between two planned towns built 400 years and hundreds of kilometers apart is itself a kind of evidence. Whatever the differences between Senusret II's pyramid building administration and Akhenaten's short, radical religious experiment, Egyptian planners in both eras arrived independently at the same basic solution to the same climate problem. Oriented streets, shared walls, and thick mudbrick construction, suggesting the principles were common professional knowledge among builders rather than a single architect's individual insight. By the New Kingdom, the individual techniques had multiplied and begun working together as a single system. At Deir el-Medina, the walled village built around 1550 BCE to house the artisans who carved the royal tombs in the Valley of the Kings. Roughly 70 houses shared a common design. Stone foundations topped with mud brick walls, exterior surfaces coated in white gypsum plaster that reflected sunlight rather than absorbing it, and flat roofs of palm wood planking that doubled as sleeping platforms once the desert night finally cooled the air enough to make the ground floor feel stagnant by comparison. One resident of this community is known by name rather than by inference. Ka held the title Chief of the Great Place under Thutmose IV, and later overseer of the works of the Great Place under Amenhotep III, meaning he personally directed construction inside the Valley of the Kings, a canyon of bare limestone with no shade, no water, and no vegetation, where daytime rock surface temperatures climb well past the air temperature reported for the valley floor beyond it. Ka's actual workday was spent inside that furnace, supervising men cutting stone by torchlight in tomb shafts that offered their own relief from the sun, but none from the exertion of the climb in and out. What waited for him at the end of that walk home was a house built on exactly the principles this account has already described. Thick gypsum white walls, a courtyard open to the sky, and a roof where he and his wife Merit could sleep once the desert finally released its heat after dark. Windows were kept small and set high in the walls, a placement that accomplished two things simultaneously. It kept direct sunlight from ever reaching the floor where people worked and slept, and it let hot air, which naturally rises, escape near the ceiling while cooler. Denser air pooled below at body height. Courtyards, standard across New Kingdom houses, regardless of the owner's wealth, added a further refinement to the system. A small planted or water-filled courtyard open to the sky created a pocket of cooler, denser air that settled downward and displaced warmer air upward and out through the high windows. A passive circulation loop requiring no fuel and no moving parts beyond the air itself, driven purely by the physical fact that cool air sinks and hot air rises. Modern engineers call this the stack effect, the same principle that pulls smoke up a chimney. And a New Kingdom courtyard functioned as exactly that, a chimney running in reverse, pulling cool air in at the bottom instead of pushing hot air out the top. Some larger New Kingdom houses went further still, digging a partial basement or cellar room beneath the main living quarters, a space that stayed close to the stable underground temperature of the earth itself, regardless of what the sky was doing above. And that served as a retreat during the hottest hours of the afternoon in exactly the way modern desert architecture still uses semi-buried rooms today. The most sophisticated addition, and the one that most resembles mechanical air conditioning, appears in tomb paintings and house models from the 18th dynasty, around the 14th century BCE, a structure Egyptians built onto their rooftops that the Arabic-speaking world would later call the malkaf, or wind catcher. It was a shaft rising above the roofline with an opening angled to face the prevailing northerly wind, funneling that wind down through the shaft and into the rooms below, before venting it back out through a second opening or an internal courtyard on the leeward side, creating a continuous draft driven by nothing but the region's own weather patterns. Combined with a wet reed mat or a porous water jar placed directly in the airstream, a cooling technique documented even earlier. In Old Kingdom tomb paintings from around 2500 BCE showing servants fanning water jars to chill a room through evaporation, a malkaf could turn ordinary desert wind into air that was both cooler and more humid by the time it reached the people sitting beneath it. The shaft itself was rarely a simple straight tube. Surviving examples and later descendants of the design typically split into two channels inside the same tower, one carrying incoming air down into the house while the other carried stale, warmed air back up and out. A bi-directional arrangement that let the system keep circulating even when the outside wind dropped to nothing. Since the temperature difference between the hot roof-level air and the cooler air lower in the shaft was often enough on its own to keep a slow draft moving. Modern instrumented studies of reconstructed and surviving wind catcher buildings have recorded indoor-outdoor temperature differences of 8 to 12 degrees Celsius from airflow alone, and experiments combining a malkaf with active evaporative wetting have pushed that gap close to 15 degrees under favorable conditions. A figure that would be a genuinely difficult engineering target for a modern building with a working compressor, let alone one built from river mud, palm wood, and reeds. What is notable about these techniques is how little they depended on the strength of the state that surrounded them. When the Old Kingdom fractured into the First Intermediate Period, around 2181 BCE, and again, when the Middle Kingdom dissolved into the Second Intermediate Period under Hyksos pressure roughly 4 centuries later, monumental construction stalled or stopped entirely. No new pyramids, no new state temples on the old scale, but ordinary households kept building the same thick-walled, small-windowed courtyard homes they always had, in the same villages, using the same riverbank mud. This was not specialized knowledge that lived inside royal workshops or priestly schools, requiring a functioning bureaucracy to preserve and transmit it, generation to generation. It lived in families, passed from one builder to the next through direct apprenticeship and daily practice, which is precisely why a technique refined under the well-funded royal projects of the Middle and New Kingdoms could survive centuries of political fragmentation almost completely intact. Nowhere is that inherited knowledge more visible today than in the Nubian villages around Aswan, where builders still raise mud-brick vaulted roofs using a technique requiring no wooden supports or scaffolding at all. Each course of brick angled to lean against the one before it until the arch closes itself. Architectural historians have traced the method directly back to pharaonic construction, and the domed and vaulted ceilings it produces are not decorative. They let hot air collect and stagnate well above head height. In a curved pocket of space, the room's occupants never have to sit inside. Egypt's kings rose and fell roughly 30 separate dynasties across 3,000 years of recorded history, and entire administrative systems collapsed and had to be rebuilt more than once. The ordinary mud brick house, adjusted only in small details from one era to the next, simply did not. Even Egypt's harshest political ruptures rarely touched the Nile's mud supply or the desert's basic weather patterns. which meant the two forces that had originally shaped the technique. Punishing heat and an abundant and renewable building material remained constant regardless of who sat on the throne in Memphis or Thebes. A collapse of central government could halt tax collection, empty a treasury, and leave a pyramid unfinished. It could not change which direction the wind blew up the valley each afternoon, and it could not make river mud a worse insulator than it already was. Political history in Egypt is usually told as a story of dynasties, wars, and monuments. The history of the ordinary house runs quietly underneath all of it, largely untouched, because it answered to the climate rather than to the crown. Native Egyptian sovereignty ended for good with the Persian conquest of 525 BCE, followed by Macedonian rule under Alexander and his Ptolemaic successors. Then direct incorporation into the Roman Empire after Cleopatra's death in 30 BCE. None of these conquests displaced mudbrick construction in ordinary Egyptian towns, since none of the conquering powers arrived with a domestic architecture better suited to the local climate. And several of them adopted Egyptian techniques rather than imposing their own. The wind catcher in particular spread well beyond Egypt's borders in the centuries that followed, appearing across Persia, Mesopotamia, and eventually the wider Islamic world under regional names, Badgir in Persian and Gulf architecture. The same Malkoff terminology carried directly into the grand merchant houses of medieval and Ottoman Cairo. Cairo's builders added their own refinement during this later period. The mashrabiyah, an elaborately carved wooden lattice screen fitted across windows and balconies, which shaded interiors from direct sun, preserved the privacy Islamic-era households valued, and broke incoming air into smaller, faster-moving currents that cooled more effectively than an open window of the same size. All while still drawing on porous, unglazed water jars set behind the lattice for evaporative cooling exactly as Old Kingdom servants had done 2,000 years earlier. A single mashrabiyah screen could take days of a skilled carpenter's labor to turn, and wealthy Cairo households sometimes commissioned dozens of them for a single house, which meant the same cooling principle Old Kingdom farmers achieved with a wet reed mat had, by the medieval period, become a luxury craft in its own right, judged as much on its beauty as on how many degrees it shaved off the afternoon heat. By the time European travelers began systematically documenting Cairo in the Ottoman period, windcatcher towers and mashrabiyah screens were among the city's most distinctive architectural features, direct descendants of the mudbrick shafts and reed screens visible in tomb paintings 3,000 years older. Further east, in the Iranian desert city of Yazd, Badgir towers eventually grew taller and more elaborate than anything built in Egypt itself, some rising several stories above the rooftops they served and cooling entire underground water reservoirs, as well as living quarters. A scale of ambition only possible once the original Nile Valley concept had been carried, tested, and refined by builders working in an equally punishing but architecturally distinct desert tradition. A building technique invented to survive one river valley's climate had become common property across an entire arid belt of the world, adopted by cultures that owed Egypt nothing politically, but everything thermally. That long continuity broke decisively in the 20th century. Industrial cement, imported steel reinforcement, and electric air conditioning arrived in Egypt as symbols of modernity and colonial-era prestige. And mud-brick construction, despite outperforming the materials replacing it in the local climate, came to be associated with poverty rather than with 5 millennia of accumulated engineering knowledge. Concrete required no local craft tradition to specify or approve, could be procured through the same international supply chains used across the rest of the 20th century world, and signaled a household's modern status in a way sun-dried mud never could, regardless of which material actually kept a room cooler in August. Government housing programs across the mid-20th century increasingly specified concrete block construction, even in rural villages, where mud brick had been the default material for longer than written history existed. And electric fans and, eventually, air conditioning units began replacing the malkaaf as the default answer to summer heat for anyone who could afford the electricity bill. It is against that backdrop that Hassan Fathi's 1946 decision to build New Gourna entirely in mud brick reads as more radical than it might otherwise sound. Fathi was not inventing anything. He was refusing to let a 5,000-year-old body of climate engineering disappear inside a single generation. At the exact moment concrete and electric cooling made it look, on the surface, unnecessary. The irony was structural as well as cultural. Concrete absorbs and conducts heat far more efficiently than mud brick, meaning many of the new government-built homes replacing centuries-old adobe villages ran measurably hotter in summer than the structures they were designed to improve upon. A trade Egyptian households made anyway because a concrete house, however uncomfortable, no longer marked its owner as poor. Comfort lost out to appearance. It would take instruments, not arguments, to reverse that trade decades later. Ka never lived to see his own house examined by anyone. He and Merritt were buried together in a tomb above Deir el-Medina, sealed, and by some accident of geology or simple neglect, never found by the robbers who stripped nearly every other tomb in the necropolis within a few generations of burial. It stayed shut for roughly 33 centuries, until the Italian archaeologist Ernesto Schiaparelli broke through on February 15, 1906, and found the couple's furniture still standing where servants had placed it. 2 separate bed frames strung with cord and linen, storage chests, cosmetic containers, and a carefully dressed wig belonging to Merritt. All of it undisturbed since the day the tomb was closed. None of it proves which cooling techniques Ka's own house specifically used. But it does something almost as valuable for anyone trying to reconstruct what his evenings actually felt like. It confirms that a foreman overseeing brutal labor in the hottest, most exposed work site in Egypt went home each night to furniture built for comfort, in a house built for shade, inside a community that had already spent centuries refining exactly how to survive its own climate. Fathi's own buildings were not an unqualified success in his lifetime. New Gourna faced real resistance from residents who associated mud brick with the poverty they were trying to leave behind, regardless of how the material actually performed. And parts of the village fell into disrepair for decades before restoration efforts began in earnest. But the underlying science he had staked his career on has since been validated by exactly the kind of instrumentation Fathi never had access to. 21st century thermal studies of vernacular adobe construction in Upper Egypt, conducted with sensors and data loggers rather than intuition and lived experience, have measured the mud brick thermal mass effect alone at roughly 3 to 7 degrees Celsius of cooling relative to outdoor peaks, with wind catcher and evaporative systems adding substantially more on top of that baseline when the two are combined in a single building. Researchers studying malkaaf performance in controlled experiments have reached similar conclusions using instrumented test cells rather than lived-in houses, isolating the wind catcher shaft's contribution from the wall's contribution and the courtyard's contribution separately. Essentially reverse engineering, building by building. A system ancient Egyptian builders had already assembled as a single working whole without ever needing to isolate the variables at all. Architectural engineer Shadi Attia, whose experimental malkaaf studies are among the most frequently cited in this field, has argued that the design deserves to be treated as serious historical engineering rather than folklore. The data backs him up. A technique dismissed as backward for most of the 20th century is now the subject of peer-reviewed engineering literature. Cited by architects designing cooling systems for climates, the original malkaaf was never intended to serve. Contemporary architects have taken the principle even further. The planned eco-city of Masdar outside Abu Dhabi incorporated a modern wind tower directly inspired by the traditional Malkoff. Engineered specifically to lower street-level temperatures in a Gulf climate, not unlike the one that produced the original design 3,000 years earlier. As global temperatures climb and electricity costs rise across the Middle East, architects and engineers are once again studying these same techniques, not as historical curiosities to be admired in a museum, but as working blueprints for a region where air conditioning already consumes a significant share of national electricity demand during the hottest months of the year. A small but growing number of Egyptian architects have begun designing new ecotourism lodges and rural housing projects in Upper Egypt, around rammed earth and mud brick construction explicitly marketed on their measured cooling performance, rather than apologized for as a budget material. A reversal of the 20th century's own assumptions about what counted as progress. Modern Egypt still lives inside the same climate that shaped its oldest buildings. The mud brick walls, the shaded lanes, the rooftop towers angled into the wind, all of it was a functioning architecture long before anyone called it sustainable design. And the questions engineers are asking about it today, chasing precise numbers for exactly how many degrees each individual technique is worth, are the same questions a builder at Cahoon was already answering 4,000 years ago with nothing more than river mud, careful shade, and a working sense of which way the wind blew.